picking up good vibrations.
In this short video, we'll learn the discrete time Fourier transform. We start by discussing some motivation for the approach we take to arrive at the discrete time Fourier transform. Then we see how this approach works for the rectangular wave, and this approach is then extended to general signals, which leads to the discrete time Fourier transform. Let us recall how we arrived at a continuous time Fourier transform. Given a signal which is 0 outside of a bounded interval, we periodically replicate it, we compute the coefficients of the Fourier series, and we understood that these coefficients are samples of an envelope function. That envelope function we call the continuous time Fourier transform. Therefore, the first question that we'll ask now in the discrete time setting is, if we have a given aperiodic function, discrete time function or signal, if it's 0 outside a bounded interval, if we periodically replicate it, we compute the coefficients of the discrete time Fourier series, will these coefficients still be samples of an envelope function?
Luckily, we have already computed the Fourier coefficients of this periodic signal consisting of the periodic rectangular wave. Thus, we can recycle this example and look at the formulas we obtained for the Fourier coefficients from a different perspective. We now note that we can write the coefficients as samples of a function that we call capital X. This function, capital X, which is the sine of omega times capital N1 plus 1/2 over sine of omega over 2, depends on omega, and the Fourier coefficients ak are obtained by replacing omega by 2 pi over capital N times k, in other words, by sampling this function x and dividing this function capital X by the period capital N. Say that we pick capital N1 equals 3. Here are the coefficients when capital N equals 20. These are 20 coefficients from k equals 0 until k equals 19. And that is all we need. But as we have discussed already, when we talked about the discrete time Fourier series, we can plot more coefficients ak. For instance, we can plot from k equals -9 until k equals 10. And this contains the same information as in the previous plot. If we plot many AKs, we know they will vary periodically, so AK is a periodic function with period 20. What happens to the Fourier coefficients AK if we change the period capital N? On the left-hand side, the rectangular wave is plotted, and on the right-hand side, the Fourier coefficients and the envelope function are plotted. An important detail is the domain where this envelope function and Fourier coefficients are plotted. This domain is, in terms of the Fourier envelope, the envelope function is from -pi until pi, and this corresponds in terms of the Fourier coefficients to coefficients that go from, let's say that capital N is even, that go from minus capital N over 2 minus 1 until capital N over 2. So we are plotting a minimal number of coefficients. Now, if we change the period capital N, we see that as we increase capital N, the envelope function multiplied by 1 over capital N is sampled more and more often as capital N increases, leading to the values of AK. The envelope function is therefore invariant to changes of period, just as in continuous time. An interesting new feature is what happens if we change the domain and plot more AKs, and also, of course, increase the domain of the envelope function. Here the domain on the right-hand side of the animation is now from -3 pi until 3 pi. Now we knew already that the coefficients would have to change periodically with k, and since they are samples of an envelope function, it is natural that that envelope function is also periodic. And this is a very interesting new feature that we did not have in continuous time. In discrete time, all the Fourier transforms will be periodic functions of period 2 pi.
We have discussed all this for rectangular waves, but this is actually a general property. The Fourier coefficients can always be written as samples of an envelope function. To see this, we just need to replace omega by the sampling times 2 pi over capital Nk in the formula for capital X and divide by capital N. An important additional fact is that the envelope function only depends on values of x over a period capital N. We can then define the Fourier transform as this envelope as we did for continuous time signals. Given an aperiodic signal, x, which is 0 outside a bounded interval, we can consider the periodic replication and call the envelope associated to this periodic replication the Fourier transform of x. Since x is 0 outside the period, we can actually take the sum as n goes from minus infinity until infinity rather than from 0 to capital N minus 1 as we did in the previous slide. This is convenient since the signal can be non-zero, for instance for negative n, and while taking the integral from minus infinity to plus infinity we can capture all the signals. As in continuous time, this formula is even valid for signals which are not necessarily 0 outside a bounded interval. We arrive at the expression for the discrete time Fourier transform. It is nothing more than this envelope we have been talking about. As we have discussed, a new feature with respect to continuous time is that it is a periodic function of period 2 pi. Although we have not talked about it, and we will not focus on it, as in continuous time, there is also a formula to recover the original signal so that there is a one-to-one relation between the signal x and the Fourier transform capital X.